general relativity step by step. If I've got a vector v, then I've been decomposing it in terms of its components like this. I've been saying v1 e1 plus v2 e2 plus v3 e3 equals, I guess, vi ei, where ei is the coordinate basis, which I'm defining as di p x1 to x3 by di xi. I equals 1, 2, 3 in this case. So P specifies the point, P is the point specified by these coordinates. I guess I could put x2 in explicitly if I wanted. Let's put that in there, x2. This is just 3 dimensions. So I've been doing that quite a lot, and I've just been denoting this whole vector as just vi. I've been denoting vector v by its components in a particular coordinate frame. Let's just say I'll get w, and this is a wj, let's say, with the indices, instead of being upstairs, they're downstairs. So what I want to do is I want to find a basis for this. But, and the bases are dead easy, I could expand it in any basis, but I want to make dot products work. Dot products are easy. Okay, so what do I want? If I've got v dot w, then the dot product is just vi wi with an implicit summation over index I. Oh, I heard it called the running index. I is the running index. Running index. That's quite a nice word. I've always called it a dummy index. Dummy index. Sometimes you see it called an umbral index, and I think I've been calling it a summed index. Different words for the same thing. Okay, so let's just do this. Let's just write it out in 3 dimensions and make sure it works. So this dot product here is going to be v1 e1 plus v2 e2 plus v3 e3 dot w1 downstairs, with the 1 downstairs, and I'm going to call it omega 1 for the first term of the basis for my covariant w, plus w2 omega 2 plus w3 omega 3, and that's got to equal v1 w1 plus v2 w2 plus v3 w3, because it's equal to vi wi. Okay, so what I'm going to do is to actually figure out what these omegas are. There's different ways of approaching this. I mean, all the books do it in different ways, and I'm just you could have argued I could have put this omega, derived these omegas earlier. That, yeah. Okay, so what that tells me is that if we have omega 1, let me write out all the terms, equals v1 w1 e1 dot omega 1 plus, because it's this term times this term. This is what we want. But if I express it, if I'm trying to find out these omegas here, I need to put the omegas back into my dot product to figure out what on earth these omegas are. See if I can do the other one now. V2 W2, so it's this one times this one, E2 dot omega 2 plus V3 W3 E3 dot omega 3. Yeah. Plus off diagonal elements V1 W2 E1 dot omega 2 plus other off diagonal elements, other off diagonal Okay? So the actual dot product, when I actually perform this dot product here, I've got my diagonal elements, which is just the first with the first, the second with the second, the third with the third, but I've got all the off-diagonal elements too. I've got the first with the second, and of course I've got all the other off-diagonal elements. I mean, I could have had something like V3, W2, E3 dot omega 2. And of course, these all have to be equal to 0. Because I want my dot product to work. So I want to, oops. Sorry about that, there's a little glitch with my interface. Yeah, I want my off-diagonal elements to equal 0. So basically, I want to identify, I want E1 dot omega 1 to equal 1 to make sure that this term here has got a coefficient 1 in front of it. And I want to make E1 dot omega, well, yeah, let's write them all out. E1 dot omega 2 equals 0 to make sure that when I expand this dot product here, this guy here disappears. I want that to be equal to 0 because I don't want any cross terms. The only terms I want are a 1 with a 1, a 2 with a 2, and a 3 with a 3. So a 1 with a 2 I don't want to happen. And of course that's going to be the case for any pair of omega 3 equals 0. E2 dot omega 1 equals 0. E2 dot omega 2 equals 1. E2 dot omega 3 equals 0. I may as well do the last line. E3 dot omega 3 equals 0. E3 dot omega 2 equals 0. E3 dot omega 3 equals 1 because I want to preserve the final term which has gone. Oh, there it is. Okay, so it's pretty clear that we've got an identity matrix here. So what I'm going to do is I'm going to write down the definition of the omegas in terms of the e's. So it's EI dot omega j equals delta ji. It's the Kronecker delta, which equals the identity matrix. Well, it's one thing to write that down, it's quite another thing to actually define it. So what I'm going to do is to go through my h theta example, and I'm actually going to find out what these omegas are in terms of the i's, but I'll do that in the next screencast because this one is already longer than I intended.